You mean here?
Can you factor out x?
And they cancel?
Yeah.
Oh, that's what I'm going to do next step.
Shouldn't it be like that minus 1 since it's, I mean, if you split up like it's negative x over x? Like, I don't, like, what do you mean you cancel the negative x?
Oh,
with that x. Oh, okay.
This x and the negative x cancel.
Never mind. I thought you were talking about the denominator.
Oh, no. Any other questions? So now we have it divided by x, so I'm just going to divide each term by x here. Okay, so I get negative x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, and so on. And now, let's express that in summation notation, and then we can integrate. So I have the sum from n equals 0 to infinity. Okay, and so now, Gretchen, I'm going to do the other way. I'm going to write the index first and then find the pattern. So if you find it easier to do the other way, you could do that too. Okay, but I purposely am starting with the summation n equals 0 because in the end, I want my answer to have the sum starting at 0. All right, so what's one thing we noticed about the pattern? Alternating, so what is negative 1 to what? It's n plus 1 here, right? Because it can't just be n, because if I plug in n equals 0, I get positive 1, but my first term is negative. However, if I have n plus 1, I plug in n equals 0 and have negative 1 to the 1, that's negative. That makes my first term negative. We're good. Okay? And it's not negative 1 to the 2n because negative 1 to the 2n is always positive since it's being squared. Okay? So, something else? X to the 2n. Okay, so what happens now when I plug in n equals 0, my exponent is 0, but here I have a 2, so what do I need to do to that now? Add 2, okay? Here I notice that all my exponents are even, so it has to be divisible by 2, and 2n plus 2 is divisible by 2, because both terms contain a 2. And also now, if I plug in n equals 0, okay, my exponent is now 2, and that's what it starts at, so we're good. Okay? And lastly, the most difficult part, the denominator. How do we express that?
2n plus 3.
Okay, good. 2n plus 3 factorial. Okay, so normally we express odd integers as 2n plus 1. Here, however, we can't express it as 2n plus 1 because if I plug in 0, then I should have 1 factorial. Okay, so I need to add 2 to get there. So I add 2 to 2n plus 1, so I have 2n plus 3 factorial. Now I plug in n equals 0, okay, and I get 3 factorial. That's exactly what I'm looking for. Okay, also 2n is even. If I add 3 to any even number, I get an odd number. So I know that this is always odd. Questions? Yes?
Can you integrate a series that the lower index starts at 1?
Yes. So you can integrate. If it starts at 1, that's fine. But again, normally we want to keep our final answer starting at 0. So if you were going to express a series starting at 1, then when you simplify, you want to change your index back to 0. So that's why I started like this.
I left it at 1 and it was just done. I don't know.
But then you're not done because then you need to simplify. Okay? Because usually on multiple choice, the index will start at 0. Okay? We like starting at 0 the best. Questions? Other questions? Okay, so now we just integrate. So I have c plus the sum from n equals 0 to infinity. Again, negative 1 to the n plus 1 stays as is because we're integrating with respect to x. Okay, so this is constant. 2n plus 3 factorial is also constant. It doesn't contain any x's. And then I integrate x to 2n plus 2 to get x to 2n plus 3 over 2n plus 3. Yes? Any questions? Yes?
Why can't you just like do stuff like between the series and not the series? Like if the series is like divided by x squared or whatever, why can't you just bring that into
Because if we were, okay, so let's just do something simpler here. Okay, say I have a series x to the n, then this would be 1 plus x squared, and so on. Okay, if I were to divide this by x squared, okay, then I've just divided each of these terms by x squared, but that's the same thing as just dividing the whole pattern by x squared, and you can see if you figure it out here, this would be sum of x to the n minus 2, and if we just divided all of these by x squared, you would see that this equals. Okay, so we're just dividing by the pattern, that's the same thing as dividing each term by term. Does that make sense?
Yeah, I mean, is that the same reason why you can integrate through this?
Exactly, because that's just the same thing as integrating term by term. Any other questions? Yes?
Why can't we split the integral into two integrals?
Oh, okay, so we could split up the numerator and then integrate each separately. However, if we did that, we would have some summation minus x, right? Because this is minus 1 and we integrate, it'll be minus x. And then you would need to simplify that. So it's not incorrect if you do that, however, it would just take a lot of changing index and exponent in order to simplify to get it into one summation. Okay? Any other questions? All right. So let's move on to limits then. What do you mean, oh no? Oh, this is going to be so much fun, you're going to love it. What is wrong with limits?
I just never kind of like making fun of it.
Oh, you will now. Okay, you totally will now. Okay, so we want to sometimes use series when we're computing limits because sometimes it'll just be easier than doing L'Hopital. And if we did direct substitution here, we get 0 over 0. Okay, so we would need to apply L'Hopital, and if we actually try L'Hopital, trust me, it would get really messy. Okay, so maybe we don't want to do that. Maybe it's just safer to use series here, and it'll be much cleaner. Okay, sometimes you'll need to do L'Hopital like 10 times, but if you use series instead, it'll come out much nicer. Okay, so either way, you'll get the answer. However, it may be cleaner and quicker to use series. So that's what we're going to see here now. So the first thing I'm going to do is convert this whole function to a series, and then I'm going to take the limit. So I'm going to convert this to a series. I need to take my common Maclaurin series and convert that, right? So I know the Maclaurin series for tan inverse and cosine, I'm going to convert that. So first of all, let's just write this on the side here. Tan inverse x, okay, equals the sum from n equals 0 to infinity of negative 1 to the n times x to the 2, 1 plus 1 over 2, 1 plus 1. And cosine x equals the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. And so I could plug these summations into the function and replace tan inverse and cosine by these summations. However, again, I want to try to cancel out terms to make things easier, so I want to actually plug in term by term. So I'm just going to find the first few terms of tan inverse and cosine, right? So again, this should be memorized, but in case you can't memorize, just plug in the first few values of n and find it. Okay, so I have x minus x to the third over